structure factor, right? Yes, we talk about structure factor, and we talk about how important that is, right? That is the basis of solving the structure, which is really the key point of doing the diffraction. And we also talk about how that gives rises to the systematic absence, right? We also talk about examples and how people use the intensity of 220 in the spin now phase to argue about the transition metal migration. What's the validation of that, right? We talk about how to use structure factor analysis to explain this, and we talk about how to do that in Excel, and we how to use a structure factor to analyze the in situ data, right? So this example is in situ heating data, and we can use the structure factor analysis to talk about what's happening in the structure when the temperature is increased. For example, the transition metal might be migrating, right? The oxygen lattice might be destroyed, and so on and on. So those things can be argued from the structure factor analysis. Okay, we'll move on to the other factors that influence intensity of the peak. So this is a simple one, multiplicity, and it's basically based on the idea that whenever you have the same despacing, you'll get the diffraction at the same angle, right? So one example in the cubic system, which is highly symmetric, you cannot tell from A from B from C, right? You cannot distinguish among them. So actually, all this set of planes, pointer. So you can see all this set of planes, they give diffraction at exactly the same position. And what that means, you actually will see a strong intensity at that position because the multiplicity is high, right? But also depending on other factors, for example, what's the magnitude of the structure factor, right? What's the Lorentz polarization factor at that point? Depending on other factors, the outcome intensity may be small or strong, but at least this term is giving a lot of a magnification of this peak, right? So this is a table listing the multiplicity for the different crystal systems, and depending on their whether it's cubic or the lesser symmetry like tetragonal, hexagonal, and so on. And also they are characterized by the HKL. So you can see for the cubic system, if this a random HKL, it was have a lot of the multiplicity, right, and corresponding a large intensity. And giving one example about that, this is not a battery material, but this material, I think it's, I use this example because I think this example is easy to understand and very straightforward. It was from a JAX paper, and there was actually a study on the peroxide as barium titanium oxide, featuring the typical perovskite structure. So what we see here, as we actually go from the high temperature and cooling down to the room temperature, right, we see the high temperature, we have one peak here, which can be indexed at 400, and it splits into two peaks. It's lab X-ray, so it's not very well resolved, but you can still tell there are two peaks, right, once the phase is cooled down. In comparison to this one, other peaks, they mostly stay as a single peak, right? We do not see obvious splitting for other peaks, but only for this one. And this is a perfect example of how multiplicity can be used to analyze the diffraction, because for this one, in the cubic system, is actually as I described in the text here, and in the cubic system, so actually this is a sixfold, right? So if we go above, that corresponds to the H00 in the cubic, so the multiplicity is 6. So that's in the cubic system. And once the structure distorts and is no longer a cubic, it changes to a tetragonal, which means that we no longer have the same A, B, C. We'll have the same A and B, AB are the equal, right? But C actually will elongate or be compressed. So so the C will be no longer the same as A and B. So that's kind of a change. So we'll be going to a tetragonal system, and I'm sorry, and we can see that once we have tetragonal, so now it goes to tetragonal, and for the H00, the multiplicity was 4, will be 4. So which means actually one peak will be decreased. At the same time, it will give rise to some kind of a 00L, which has a lower multiplicity, a lower peak. But you can tell either the H00 or the 00L in the tetragonal, they cannot be distinguished in the cubic system, right? You cannot tell from A from C. So you cannot tell whether it's H00 or it's 00L, right? You cannot tell from A, B, or C. So they degenerate in cubic and have the multiplicity of 6. But once it's tetragonal, we can tell H00 from OOL. And the former one has a multiplicity of 4, and the latter one has that of 2. And that is the case what is happening here. And this peak was split because A, B, and C are no longer equal. And it were split into 2 peaks with the peak ratio around 2.1 for these 2 peaks. So this is, I think, it's a good example of how you can apply the knowledge about the multiplicity to analyzing X-ray diffraction. We also have some examples of our own work. So this is some thermal stability study we did some time ago. It was published in JAX. It was in collaboration with Ichigino from SLAC. And this is typically we observe when we're heating up the charged cathode, which originally have this kind of layer structure. And then as we heat up the sample and kind of simulating what is going on when there's a thermal runaway in the battery system, right? So when there's some safety issue causing either shorting that leads to a thermal runaway, and then actually their cathode will be heated up. And I didn't show their mass spectroscopy here, but typically that will go through some oxygen release, which is very dangerous as we have some highly flammable electrolyte in the system, right? That's the background. But let's focus on the cathode itself. So the phase goes through, starting from layered and goes through to the layered and spinel, and then to the spinel and rock salt. So you see this kind of trend, right? It's going from layer to spinel and rock salt. And then you see some kind of peaks. Originally have 2 peaks, they start to merge, right? So that's kind of an opposite way as we showed in the previous slide. In the previous slide, we have a high symmetry here, which is cubic, and then it splits into the lower symmetry, which is tetragonal, right? And the peak ratio can be analyzed by the multiplicity. And now we are going in an opposite way. We have a lower symmetry, and then we have a higher symmetry. Then we have the merging of the peaks. So this is this is not too much about the multiplicity, but just some kind of something related to the battery work, right? So typically in the phase transition, the rule of thumb is the higher the temperature, the higher the crystal symmetry. And this is showing that we have the layered at room temperature, and once we heat it up, we have the spinel, which is cubic, and having higher symmetry than the raw material one. And then we keep heating it up. Actually, when we reach a very high temperature, we can reach the rock salt phase, which is based on the FM3/M, which is even higher symmetry than the spinel symmetry. So this is general rule of thumb that the higher temperature typically leads to higher symmetry of the crystal. And this is also true for the material synthesis. So for example, if some material is cubic, even without knowing the details of the synthesis condition, I would guess it requires high temperature to synthesize this kind of material, right? So yeah, just something that's related. Okay, back to Charles' question last time. So I think Charles asked a very good question, and Yeah, I try to use my best knowledge at that time to answer the question, but when I review the slides, I realize actually I don't think I really answered clearly. So I'll try my best this time to answer it very clearly. So first we need to talk about what is polarization, right? So I think this picture is more illustrative. So as everybody understands, X-ray itself is also just like any electromagnetic wave, like visible light, ultraviolet or infrared. Any wave, electromagnetic wave, has both the electric the wave and the magnetic wave, which are coupled together, right? This is something that was taught in the physics of high school. Okay, and the typical light, when it is not polarized, so actually we had this kind of electromagnetic wave in all directions. So typically in the physics, actually, they can be just described by one vector showing the direction of this wave. So we do not draw the magnetic wave here, just to make things more clear and to see. So this is only showing the electric field. We can see the natural light typically gives uh, the the electromagnetic wave oscillating in all directions, in many kinds of directions, right? So if you have a polarizer, this can be something like, for example, the sunshades you can buy from shops, and some sunshades would have a label saying polarize on the shades. So actually, they will cause some polarization of the natural light, or it can be caused by some typical solution of the chemicals, right? So in the chemistry, we learn about how the chiral structure can give rise some, directional polarization of the light, right? So
Yeah, sorry to interrupt. There is a typo. So only electric field show, not yield show.
Oh, field, right?
Yeah. Okay.
Thanks, Jim. Yeah.
Sorry.
Yeah, I'll correct this after the lecture. Right. So it can be, either the gas or the solution, when it's polarized, and so it's kind of filter out certain the electromagnetic wave, such that we can only observe the electromagnetic wave in specific direction, right? So this is polarized, and this is in the context of some kind of a more like either the light from the lamp or natural light. But for our experiment, we're you're already talking about the X-ray, right? But the general principle still applies. And we need to be aware that the synchrotron itself, it has a capability of producing highly polarized X-ray. So it's not like the conventional lab X-ray that has this kind of a non-polarized feature. So for the synchrotron, you can imagine what we get is something more like this. It's polarized in one direction, 99%. Yeah. And the second point is about how the polarization really relates to the peak intensity. So this is the picture I really like. I think this is the most clear picture I've ever seen on a website. So this is from this website. I took more points about this. I do encourage you to check this website. Use it as a dictionary whenever you have questions about the powder X-ray diffraction. It's an excellent online course. So this picture is from this website. So we can look at the two extreme cases. So one case is, let's say we still have the polarized the X-ray coming, right? So and somehow this polarized ray is in a specific direction that it's in plane with the diffraction plane. So what is diffraction plane? Diffraction plane, you can imagine, so we can have an atom here or have electron here that is diffracting this X-ray. Now we're causing this X-ray to be diffracted such that actually will be diffracted in this direction, right? So we'll have this kind of plane. And in our specific case, it is the slides or the screen we're looking at, right? So the screen is a plane, and the screen is the diffraction plane. If incoming X-ray is in plane with the diffraction plane, it will have this kind of a relationship. And this vector is actually simply have the cosine 2 theta relationship with the original one. And because their intensity is kind of like the square of the magnitude is kind of square of the amplitude, right? So that's why there's a cosine 2 theta square relationship if we're talking about in this case. Another extreme case is the incoming X-ray is perpendicular to the diffraction plane, right? So it's actually diffracting in this way. The diffraction planes are still the same, they're still the screen, but because our incoming wave now is in this direction, you'll be diffracted in this way. And there's no reduction in intensity. We're totally conserve the intensity of the incoming X-ray. So the ratio is 1. And in the practical situation, we typically encounter 2 cases, one in the lab X-ray, one in the synchron, as our group to speak. For the synchron, we are talking about this specific case of the that we have the no intensity reduction. We have the ratio of diffraction X-ray that is in the ratio of 1 to the incoming X-ray. For the lab X-ray, because it's not polarized, so actually the hybridized of these 2 variants. So it has some intensity falling into this category. It also has some their directions that fall into this category. So the final result is actually just simply the combination of them, or the average of these 2 extreme cases, and that's the intensity reduction in the specific case of a lab X-ray. And you can see this term is introducing some 2 theta dependent factor that will influence the intensity observed, right? And you can imagine when the 2 theta is 90 degrees C, this is a very small number. So at 90 degrees C, we'll see some additional reduction of the peak intensity if the diffraction angle is at 90 degrees. So that's something very specific to the X-ray diffraction, and maybe something not intuitive, I think. And like I said, you can check this website, and they have more detailed description. But ideas, I think, something I present here. And also back to Ding's question, I think Ding, in fact, you asked a very good question, and also, I don't think I really answered your question clearly last time. But I would encourage you to go to this website. This is actually some lectures put online by Lysos 2. So they're covering different topics, ranging from imaging, spectroscopy, to scattering, or even more advanced techniques. And also they have one section, one lecture dedicated to their description of synchron radiation. So I think this lecture, this slides, they have a very detailed description about the answer to your questions. But the short answer here is indeed the polarization. How the beam is polarized is really dependent on the device, the beam line is used. It is bending magnetic, or it's undulated, or it's weaker. So actually the different devices will give rise to different detailed polarization, right? So, but coming back to the point we're interested in, we can understand to the level that synchron X-ray will give rise to highly polarized the X-ray, and then we'll talk. I'll show how that translates to some practical application. So, for example, when we do the real refinement, what kind of parameters we should use based on this kind of knowledge, right? So I think this lecture will give the details, but at this time, we can't be satisfied with knowing that synchron X-ray give us a highly polarized the X-ray that equals the ratio almost equals to 1 in all cases. Okay. And the next one is something I also want to clarify. I think in my previous slides, in the slides I sent you last time, I think I put the Lorentz factor in a different slides, which I said it relates to the diffraction geometry, to their beamline setup, to their radiation source, and so on and on, which is not correct. Yeah, and I'm partially to blame, and I think I can be partially be excused, but because I realize actually in the community there are so many people who misuse this kind of two terminologies, polarization factor and Lorentz factor. So they're misused many times, and I'll explain why in the next slide. But this one actually has a more origin of the physics of diffraction, which we didn't really cover in this lecture. But if somehow you happen to already know what is the Edwards sphere and the reciprocal space, you know that diffractions, theoretically, diffractions happens only when the Edwards sphere is intercepted. Also, they have interception with the reciprocal space. So we see the points here, right? And then this will actually give rise to a diffraction. And we know each point in the reciprocal space corresponds to HKL planes in the real space. So that means this HKL will give rise to diffraction. That's ideally the case. But later people realize that's practically what is really happening, that this Edwards sphere has certain kind of a thickness. It's not like infinitely thin layer, but it has certain kind of a thickness. And also, instead of having the perfect spots, just one single dot, actually this reciprocal space would comprise of this kind of a little bit smeared spots. So for this point, in principle, it will not interfere with, not intercept the Edwards ball here, sphere, right? But in practice, you see there's a slight overlap, and that contributes to the intensity. So what Lorentz factor is basically describing how this kind of phenomenon, and this is, as you can already guess, this is also a two-theta dependent phenomenon. So that's the message I want you to understand at this point, right? You need to know this Lorentz factor relates to the imperfection of this kind of interception between reciprocal space and the Edwards ball sphere, and more importantly, is two-theta dependent. And that's probably if you do not want to get too much confused, then I think that's the key message you want to know at this point. And also, this website gives you a more detailed description. And if you want to spend more time, you're welcome to do that and check all the details of what I said, right? So this is the point I want to clarify. And because Lorentz factor and the polarization factor, they're both two-theta dependent. So in the real refinement, we always group them together and call them as simple one factor, which is a short-term as LP factor in many of the softwares. But you can see a lot of people actually just call this factor polarization. And also, I think I'm one of them who actually have the impression that this factor simply relates to the polarization of the beam, which is not very true, right? As we have already went through in the previous slides, it has two contributions, both from the polarization of the beam and also from this kind of diffraction geometry that relates to the that explained in the Lorentz factor. Okay, so the Lorentz polarization factor is simply a combination of these two, since they are both dependent, and you can still see this kind of term, which might sound familiar to you, right? When we talk about one of the extreme cases in the polarized beam being diffracted. And this term simply comes from the computation of the Lorentz factor. And you see, simply this one is replaced by 1 for the synchronous case. And you can recognize the whole term is actually a combination of both the polarization factor and the Lorentz factor. And this figure is what I showed in the previous slides, which was not correct. But the data is correct. It's showing how this LP factor influence intensity that you observe. So in the software that you use to carry out real refinement, as I said, we always aim to obtain the correct structure factor. And the key to do that is we make corrections for other factors, right? And one of them is LP factor. So we need to correct the LP factor and what that it does to the intensity to really to get to the final correct intensity for the structure factor. So that's really the purpose of doing this correction. Okay, and yeah, this is from previous slides. I think this sentence should be explained more clearly in the next slide. Okay, so now we know what LP factor it is. Then what does that have to do with our practical application? So depending on the software we use, either Topaz or the GSAS, GSAS is free, and I think it's maybe more popular. And Topaz is a commercial, but we do have the academic version, which is much less expensive than the commercial one, but still costs thousands of dollars, something. Depending on the software we'll be using, and so actually they're be treated differently in the two softwares. So I'm listing this kind of table here. So you see when you're using the lab X-ray data, you should be using the LP factor 0. What 0 means is telling the Topaz to insert the function that was that has a kind of the labeling is called the the parameter, the 0 parameter in that function. And similarly, 90 describes the parameter that we used in the same function, but the parameter changes from 0 to 90. You can check this detailed PDF. This was written by the author of the Topaz software, Alan. So Alan systematically compared how LP factor is treated among 3 softwares, Topaz, GSS, and the Foolproof. Because I've never used Foolproof, so I didn't really put Foolproof here, but I used to use GSS quite a lot and also Topaz quite a lot recently, so I just list these 2 softwares. Alan gave very detailed comparison among the functions and the meaning of the parameters in this PDF file. You can directly copy paste in your web browser and download it. So the conclusion is when you use Topaz, you use this parameter for the different radiation, and when you use GSAS, you use these parameters for the setup. Okay, and IPOL in GSAS simply means the type of function. So this is the type 0 function that is used to treat this LP factor, and this is a parameter that should be used when you are dealing with the lab X-ray. And this is the parameter used when you're dealing with synchrotron. If you input the parameter not in the correct way, then you will have trouble fitting the data. So I think this is also has some relevance to the quality of your fitting, also the success of your fitting, right? Okay, so I think that's yeah, that's pretty much what I want to say about LP factor. Is there any questions before we move on? No?
Oh, Aaron, I have a naive question. When you talk about the polarization, you said there are 2 extreme conditions.
Right.
So I'm a little bit confused why the intensity remains in 1 if it is perpendicular even after the diffraction. As long as there is a scattering happening, I assume the intensity will be decreased.
I don't think that's a naive question. I think that's a pretty good one. My understanding is, yeah, we can also talk further on this, right? Maybe even after this lecture. My understanding is, so if you look at this case, you see the diffraction, the incoming one is actually the inner plane, right? So actually it's kind of like a vector that has their, then it will actually will diverge into 2 directions. So we have incoming vector here, but it will actually be decomposed into 2 directions. Then it has this kind of vector in this direction. But what is showing here, actually, because this vector will not actually decompose, will not have decomposition in this direction, right? Everything actually will be maintained in this direction. Well, Well, I'm still explaining to you. Actually, I cannot fully convince myself that I'm 100% sure of the picture here. But for the time's sake, I think at least we can accept this conclusion. This is a valid conclusion. The orange of this, we probably we need to dig more.
Okay, I will also check the website.
Right.
Thank you, Adrian.
And if you find out the answer, you are certainly you're welcome to share with everybody else, right?
Sure.
Right. Okay. So no question from anybody else? Okay, then we'll move on. So yeah, so this is the website I just mentioned. This is actually an online course from University of London, and by far this would be the most inclusive, clear, and practical online course I've ever seen. So I've seen many online courses, but I think this is really the best one. I highly recommend. And as I said, you can basically use it as a dictionary for other questions you meet, right? When you're trying to either understand the direction or to practical application of it. So yeah, this is a website. You can make a note of that. We can move on to the atomic displacement parameter. And this is also short term as their ADP. But sometimes people also call anisotropic displacement parameter as ADP. So you'll see as sometimes in literature. So just want to clarify that we do not make any confusions. We're firstly talking about the A stands for atomic in our case, right, in our lecture. But you should appreciate that sometimes A also stands for anisotropic, right? So yeah, just to be aware of that. This ADP is also important. It's for us to understand the intensity of diffraction. So basically what it does is dampening the intensity. But we need to understand its origin. The origin of ADP comes actually from two parts. So one thing is from the thermal part, or the vibrational part. The other comes from the static part. Or we can say it's a position distribution, right? So we know the atoms, they are not still. They're doing the vibration all the time. And but even in the rigid framework, as in the case of crystal, even though we picture the atoms, they are fixed in the specific positions, but still actually they're going through their small vibrations, right? So this one actually gives the uncertainty of the position at a specific time. Is kind of smearing out the real position of the atom. The second part comes from the static, the distribution of the atom position. So let's say, for example, we have a crystal and we know the position of each atom, and the one atom may have the position like 0, 0, 0.5, right? So xy equals 0 and the z equals to 0.5. But if we count, let's say 1 million atoms, then not all of them actually will fall exactly on 0.5, even without considering the thermal vibration. Let's say we just cool down the sample to a very, very low temperature, so the thermal vibration can be negligible. Even in that case, the atoms, they are not perfectly hanging on their perfect position described by the Wyckoff side position. It's very likely we'll see some atoms like 0.5 or 0.01, some pattern atoms in 0.5 over 2, and some patterns in maybe in 0.49005 something. Anyway, but if we have a very large amount of atoms and we count their positions, and in most of cases, not all the cases, most of cases, they would form some kind of Gaussian distribution, meaning that most of atoms, they do actually, they're almost lying on the exact position, but once actually the position is a little bit off the perfect position, the number of atoms will, or the percentage of atoms in the total atoms will sharply fall off, following a kind of a Gaussian distribution. And in fact, this is actually the basis of how to mathematically treat this kind of disorder from both the thermal part and the static part. So what I mean is now people actually can treat this kind of disorder by using this kind of formula, but this is really in fact based on assumption that the static disorder rigidly follows a Gaussian distribution. But as I mentioned, this is mostly true, but not always true. In some cases, it's not true. So in fact, even the basis of the diffraction physics cannot really describe all the intensity. Or in other words, you will never find a way to really perfect fit your data, right? So, but in most of the cases we encounter, we can be satisfied in knowing that, okay, this is a very good description of the disorder and integrates both the thermal part and the static part. And you can tell this is kind of a Gaussian distribution function. And so we'll see how that does to the intensity. So this is a calculation, and this calculation is easy to do, right? Since we already know the exact expression of the function, we can simply plug in the numbers for the b value, then we can calculate how that varies at the term of 2 theta. But now we put actually the kind of scattering vector, as I mentioned, which should be used to the interchange between scattering vector and 2 theta, right? So this is, you can also see this is dependent on 2 theta. So if b is close to 0, meaning that there's no thermal vibration, there's no static disorder, then there is doing nothing to the intensity. But once we have a non-zero b value, it will actually will cause intensity fall off or intensity reduction at high 2 theta angles, right? So generating a diffraction pattern that we typically observe. So we typically would observe a high 2 theta at a high intensity at low 2 theta angles, and as the 2 theta increase, we observe the peaks are becoming more and more weak, right? Weaker and weaker. So we see this kind of very weak peaks. But in fact, if you check more carefully, you can also see the peaks are getting more broad, right? But we'll come to the broad part later in the lecture. But at this time, we know the intensity is decreasing. And if you remember, another term is also causing this kind of a intensity reduction as a 2 theta increase. Does anybody remember what that is? We talked about another term causing the. Anybody want to type? Okay. Pretty silent. Or somebody already typed it? Okay. Anyway, I couldn't see the chat. Maybe somebody already typed in the chat. But yeah, the other factor is atomic scattering vector, right? You remember that the scattering of an atom is also 2 theta dependent. And for X-ray, that's also decreasing as the 2 theta increases. So we can see for the X-ray diffraction, both atomic scattering factor and also the ADP, or the atomic displacement parameter, they're causing this kind of overall intensity reduction in the final diffraction pattern, right? So this could be regarded some kind of a limitation of X-ray because we really want to see clearly their high angle peaks. Okay. And this note here, and the ADP dampening is valid both for X-ray diffraction and neutron diffraction. Because I mentioned this because for the atomic scattering factor, it is not 2 theta dependent for the neutron diffraction. So for neutron, because it is interacting with the nuclei, so actually there's no change of intensity with regard to the atomic scattering factor. But for neutron diffraction, this ADP is still valid, right? Because there's thermal vibration and their static disorder, that's still valid. So you still have this kind of decrease even for neutron, right? So this is a universal for both X-ray and neutron. Okay. And we'll talk a little bit about absorption coefficient. And this is also, we're still actually still in the context of talking about the peak intensity, because I think that's probably maybe the most complicated, but also maybe the most important thing about the X-ray diffraction. And we are going through all the terms that's making contribution, either intensify or reduce the intensity of X-ray peak. And one of them is absorption coefficient, which is basically surely reducing the intensity, right? So this picture is giving some kind of idea how the X-rays matter. So once even though we're doing the X-ray diffraction pattern, right? But surely the X-ray doesn't really obey our order and just devote all its efforts to diffraction. It's interacting with the sample in many ways, right? So, and also that gives us a chance, surely in another way, it gives us a chance to use different detectors and to monitor different interactions, then we get a different information, right? But also this means only a portion of the X-ray actually will finally gives contribution to this route, this elastic, the scattered X-ray, right? So this is the only one of them. So we need to make corrections, and we need to consider other process. And one of them is something we are already familiar with, absorption process. Our sample is absorbing the incoming X-ray, right? So even though we're doing X-ray diffraction, it's still absorbing. Just that we didn't really measure this kind of absorption coefficient, but the thing is happening. And we need to consider that, especially we want to make a choice of the radiation. For example, we have some sample, we may say we do not have enough synchronous time as time. Is it appropriate to simply just to do a lab X-ray, couple K alpha radiation on the sample and do the refinement? The answer may be no, right? And the same is also true for synchrotron. We have some synchrotron time, and we have some specific sample, and we cannot always presume that synchrotron is the best radiation for this sample. It may not be true, right? So, and that practically that relates to the calculation of this the muR value, and this muR value is also something that you encounter in the X-ray diffraction software, and also something I'll show in the next slide. You can use online website to do the calculation. The example here is given about the lithium nickel oxide, a typical battery cathode material. So we can determine what is really the good wavelength for measuring the diffraction of the lithium nickel oxide, right? So you can go to this website. This is basically, you can tell it's a 11 BM website of their APS. It provides this nice way to calculate whether the radiation that you use is appropriate for a sample. And we do that, if you go to that website, it will ask you to input the chemical formula of the sample, right? For in our case, is this nickel oxide, and also something like the packing density. If you do not know, you can check some of the empirical numbers. They're good enough, right? And also something like the porosity of the sample. You can also make some estimation. After you input those parameters, this website will generate this kind of diagram for you, or this kind of figure for you to understand. So for example, we input the information for nickel oxide, and we have this kind of figure. And let's say we want to use a radiation of 1.14, which is actually close to the copper K alpha, right? Copper K alpha is like 1.54. But some beam lines provide this kind of value. It's not some hypothetical, right? It's actually sometimes it comes, the beam line does have this kind of value. We can see this muR is as large as 10, around close to 10 at this wavelength. So that means there's too much absorption from the sample. And the absorption is so large that no software can really make a meaningful correction of absorption coefficient. So software can make corrections. They can consider the absorption coefficient, but as long as the absorption is negligible or within the extent that can be modeled mathematically. Once actually there's too much absorption and there's no way to really describe them, so there's no way to also, to get the correct diffraction intensity. So this is too large, and number one is kind of like a threshold where we need to be aware of, right? And if we use a very short wavelengths, this is wavelengths for the things for 11 bm and also for the 17 bm at APS. And you can see now we have a very small UR value, meaning that the X-ray is almost penetrating through the sample. There's a negligible absorption from the sample about this X-ray. And then this is the ideal radiation for doing our experiment, right? And you may say, okay, this is not surprising since we're using 3D transition metal and we're using high energy X-ray, right? So it should be penetrating this sample. But the other thing is, if we somehow measure some heavy elements, for example, containing silver or containing molybdenum or containing, let's say, lead, some very heavy samples, then we need to be careful about these short wavelengths. Because in that case, actually the sample could be absorbing if we use the short wavelengths. And in those cases, it might be more appropriate to use the long wavelengths radiation, right? So we can have some kind of a raw thumb guess even before we do the detailed calculation. Okay. I think we probably, we can stop here. Today's lecture a little bit short. Maybe it will last about 40 minutes something, but because the next one I think really requires some more real effort to really go through it. Next time we're talking about the peak shape, which also I think requires some detailed explanation and some detailed examples. I guess one lecture probably is required to go through this. So maybe we can stop here today. And as always, you're welcome to ask questions.
Hi, this is Steve. Just wondering, when we are calculating muR, can we relate that to like a transmission rate or?
I mean this one?
Yes, yes.
Are you saying that this is kind of like reciprocal of the transmission? Is that what you mean?
Or like in synchrotron X-ray, like we can compute the X-ray transmission rate when we are doing like fluorescence. Just wondering.
Oh, right. Yes. I think there's another website. I'll find it and I'll send you later if I still remember it. I think that's based on NIST. NIST also has a website that you can input the formula, and also it can actually help you to calculate how much it will be transmitted.
Thank you.